What if everything you see, touch, and know is just a tiny fraction of reality? Imagine a cosmic force so powerful, it sculpted galaxies, yet remains utterly invisible to us. For decades, scientists have been hunting for this elusive architect of the universe, dark matter. Are we on the verge of unmasking its true nature? The universe as we know it is lying to us. Nearly 85% of its very fabric is missing, yet its gravitational pull dictates the fate of every star and galaxy. This isn't a sci-fi fantasy, it's the profound mystery of dark matter, the unseen force that builds our cosmos. Get ready to have your understanding of reality challenged. Think of it like an unseen hand guiding a puppet show, perfectly orchestrating every movement, yet never revealing itself. That's dark matter, the invisible architect pulling the strings of our universe, shaping galaxies and clusters, all while remaining a ghost. Join us as we journey into the scientific quest to finally reveal this cosmic enigma from observation to theory. The journey from anomaly to a fundamental component began the moment scientists noticed that something subtle, something stubborn, refused to fit inside the tidy predictions of their established models. In the early days, these observations felt like little whispers, small mismatches, faint irregularities, measurements that insisted on nudging slightly beyond the margins of certainty. Researchers tried to attribute them to instrument noise, calibration mistakes, or simple human oversight, yet the inconsistencies returned with the persistence of a quiet truth waiting to be acknowledged. Over time, the anomaly became impossible to brush aside, not by growing louder, but by growing steady, appearing across different experiments, different teams, different continents, weaving a soft but undeniable thread through the fabric of scientific data that demanded attention rather than dismissal. As the anomaly settled into scientific awareness, it began to reshape the curiosity of those who observed it. For a while, teams repeated their measurements with almost meditative patience, refining their instruments, rethinking their procedures, checking the purity of materials, the stability of temperature, the consistency of fields, all in the hope that the stubborn discrepancy would dissolve. Yet the discrepancy remained as loyal as a shadow. Its refusal to disappear signaled something that all good science eventually welcomes: a crack in the wall where new light might enter. This realization changed the tone in laboratories around the world, shifting the focus from chasing errors to listening for meaning, as if the anomaly itself were trying to speak through the layered silence of equations. The process of moving from observation to theory always begins with doubt, but it blooms through wonder. When researchers finally allowed themselves to wonder, they started imagining possibilities beyond the comfortable boundaries of the models they had trusted. They filled chalkboards with equations that pushed familiar concepts into unfamiliar corners. They tested mathematical frameworks that stretched old assumptions without breaking them. They tried to see if the anomaly could fit into existing theories through clever reinterpretations, but like a puzzle piece carved from a different set, it resisted being forced into place. It needed not reinterpretation, but recognition and acknowledgement that the universe was offering a new piece entirely. As these thoughts deepened, the scientific community began to form small clusters of hypotheses. Some proposed exotic particles. Some imagined hidden interactions. Others speculated that perhaps something about space-time itself carried subtle behaviors yet unaccounted for. Each idea arrived tender, uncertain, shimmering with potential but fragile in details. No one could declare certainty, but the questions grew rich, the atmosphere electric. Every researcher knew that somewhere within these speculations lay the seed of a theory waiting to bloom, one that could elegantly explain both the anomaly and the broader tapestry of known physics. What made this phase both exhilarating and humbling was the delicate dance between imagination and restraint. Scientists had to allow their creativity to roam without letting it outrun evidence. They had to remain grounded in mathematics, disciplined in logic, yet open to possibilities that felt almost poetic in their strangeness. Each day brought new calculations, new simulations, new proposals passed quietly between colleagues before being shared more widely. And through it all, the anomaly lingered, a silent guide pointing toward a frontier that had always existed but had never before been illuminated. Meanwhile, parallel experiments in distant labs began reporting results that echoed the original anomaly. This repetition did more than strengthen confidence, it braided the anomaly into a unifying thread that connected isolated disciplines. Astrophysicists, particle physicists, condensed matter researchers, each found hints of the same quiet deviation. The universe, it seemed, was humming a faint melody that different instruments were finally learning to hear. That melody transformed the anomaly from a local glitch into a global clue, suggesting a deeper principle weaving its way through the structure of reality. With this growing consensus, theorists intensified their work. They revisited symmetrical frameworks, questioned conservation relationships, and probed the boundaries of unification theories. Every potential explanation was tested with rigorous skepticism. Did it preserve the successes of established models? Could it accommodate all observed data? Did it demand assumptions too extravagant to be credible? In this careful filtering, weak ideas fell away, allowing stronger, more coherent possibilities to rise. The anomaly had become a compass, and theory was beginning to follow its direction. Eventually, one particular interpretation began to resonate. It was not the flashiest, nor the most revolutionary, but it held an elegance that caught the attention of the community. It explained the anomaly with graceful consistency, connected previously unrelated observations, and opened pathways for predictions that could be tested. Like a melody resolving into harmony, the theory stitched scattered data into a cohesive framework, offering a lens through which the anomaly no longer looked like a misfit but like the missing part of an intricate picture. Even so, acceptance in science never arrives suddenly. It grows slowly, patiently, with each successful test. Researchers designed experiments specifically tailored to probe the predictions of this emerging theory. They refined detectors, developed new analysis techniques, and gathered data with painstaking precision. Every positive result added weight to the theory, while every ambiguous one prompted refinement. The journey from anomaly to understanding became a testament to the discipline and devotion embedded in scientific progress. As evidence accumulated, excitement quietly blossomed. Conferences began dedicating sessions to the topic. Graduate students wrote theses exploring its implications. Papers flowed through peer review with increasing sophistication. The anomaly was no longer something mysterious to be explained, it had become a doorway that opened into deeper layers of the universe's architecture. Stepping through it required courage, humility, and collaboration, qualities the scientific community embraced with renewed unity. This transformation also changed the language scientists used. Instead of phrases like unexpected deviation, they began using words like signal and signature. Instead of describing the anomaly as a problem, they spoke of it as an opportunity. The once fragile interpretations gained structure, depth, and mathematical beauty. Theory, once only a whisper, now stood like a growing pillar supporting new understandings of nature's laws. As the theory matured, it revealed its capacity to predict phenomena that had never before been observed. These predictions served as the ultimate test. Experiments were launched, instruments tuned, collaborations expanded. The predictions acted like stars guiding the journey, their verification serving both as confirmation and celebration. Each new result intertwined with the theory, reinforcing its place in the scientific landscape. The path from anomaly to fundamental principle is not merely intellectual, it is emotional. The scientists involved felt the quiet thrill of participating in something larger than themselves. They sensed the unfolding of a story written not by human imagination alone, but by the universe itself, revealing secrets step by patient step. The anomaly had become a teacher, guiding humanity one question at a time toward a broader horizon. In this journey, failure played just as important a role as success. Many ideas that initially seemed promising collapsed under scrutiny. Yet each collapse clarified the direction forward. Just as a sculptor removes excess stone to reveal the figure inside, these discarded theories carved away what the universe was not, helping scientists approach what the universe actually is. Over the years, the once small anomaly evolved into a well-defined effect with measurable consequences. What was once a curious deviation had grown into a cornerstone of understanding. It influenced how other models were constructed, how experiments were designed, how cross-disciplinary studies were connected. It served as a reminder that even the tiniest whisper in data can herald a vast realization. Researchers began building new technologies inspired by the theoretical insights the anomaly had provided. Just as quantum mechanics had enabled modern electronics, this new principle showed promise for shaping future innovations. Although still in its infancy, it hinted at possibilities, ranging from advanced sensors to deeper probes into cosmic structures. The anomaly had moved from theory to utility, shaping the tools of tomorrow. Yet the heart of this journey lay not in application but in comprehension. The anomaly had invited humanity to rethink assumptions about the universe's architecture. It encouraged reconsideration of what was fundamental, what was emergent, and what remained hidden in the vast, silent corridors of space-time. The theory that grew from it carried both elegance and humility, acknowledging the limits of knowledge while stretching those limits outward. In moments of reflection, scientists involved in the earliest observations would look back and feel awe at how far a tiny inconsistency had carried them. They remembered the initial skepticism, the quiet persistence, the long nights of recalibration, the shared belief that meaning could emerge from the smallest signs. Their story mirrored the larger human journey, learning to listen, to question, and to follow truth even when it begins as a whisper. Over time, textbooks were rewritten. Diagrams were updated. New generations of students learned the principle not as an anomaly but as an ordinary part of the cosmic order. What had once been strange became standard, woven seamlessly into the foundations of education. The theory found its home not only in research papers but in the minds of those just beginning their scientific journeys. Yet even in its acceptance, the theory preserved its mystery. Like every discovery, it opened more questions than it answered. Scientists began exploring irregularities within the new framework, small deviations that suggested there were deeper layers still hidden beneath the surface. The cycle began again: observation, anomaly, curiosity, and the gradual shift toward new theories. This continuity is what makes the scientific journey unending. Each anomaly is both an end and a beginning, a conclusion to old assumptions and an invitation into new ones. The anomaly that began this story had not only reshaped theory but had reminded the world that knowledge expands from the edges where certainty falters. In the end, the journey from observation to theory became a quiet celebration of patience, perseverance, and the gentle persistence of truth. It illustrated that progress does not always thunder forward, sometimes it moves like a slow tide, shaping the shoreline grain by grain. And through that gradual shaping, the anomaly found its place as a fundamental component of the universe's symphony, guiding science toward deeper understanding with the steady grace of something that had been waiting to be discovered all along. The gravitational riddle, why galaxies spin too fast and clusters don't fly apart, became one of the most unsettling discoveries of modern astronomy, not because it was loud or dramatic, but because it was quietly impossible to ignore. When astronomers began measuring how stars moved around the centers of galaxies, they expected to see the elegant decline predicted by Newtonian dynamics, a graceful slowing of orbital speeds with increasing distance. Instead, they found something stubbornly flat, almost defiant. Stars on the outskirts were spinning far too quickly, moving with a confidence that the visible mass simply could not justify. According to classical gravity, those galaxies should have torn themselves apart long ago, flinging their outer stars into the cosmic sea, but they hadn't. Something unseen was holding them together. This mystery deepened further when scientists extended their gaze to galaxy clusters, the sprawling congregations of hundreds or thousands of galaxies bound in vast celestial webs. These clusters behaved as though gripped by an invisible force, their galaxies moving with a liveliness too energetic for the meager amount of observable mass. The gravitational accounting simply didn't add up. The motions were too wild, too free, too bold to be contained by the mass that telescopes could see. It was as if the universe were whispering that its true weight was hidden behind a veil, an immense but silent presence shaping everything without revealing itself. Astronomers first suspected that perhaps they were missing faint stars or dim gas, some overlooked population of ordinary matter that could compensate for the missing mass. But even after sweeping the skies with instruments sensitive to every wavelength, radio to gamma, they still came up short. No amount of faint stellar light, cold hydrogen clouds, or dust-laced nebulae could account for the enormous gravitational grip holding galaxies and clusters intact. The deficit was too vast, the riddle too persistent. At this point, the problem ceased to be a mere observational quirk. It became a crisis, a deep wound in the mathematical fabric of astrophysics. The universality of gravity, one of the most trusted principles in science, seemed to be questioned by the very things it was meant to describe. Galaxy rotation. Curves refused to obediently follow the predictions. Cluster dynamics looked chaotic yet mysteriously stable. The cosmos appeared to be playing by rules that were both familiar and alien. Some researchers began exploring possibilities rooted in unseen matter. They imagined clouds of non-luminous particles, transparent, odorless, silent in every electromagnetic sense. This matter would interact through gravity but remain invisible to telescopes, filling the universe like a ghostly scaffolding. It was an audacious idea, one that required accepting that most of the matter in existence was not like us, not atomic, not chemical, not starlit. But despite how strange the idea was, it fit the gravitational puzzle more cleanly than anything else proposed. Others, however, wondered whether the fault lay not in matter but in gravity itself. Perhaps Newton's laws, so elegant and reliable on human scales, began to drift into new territory at galactic distances. Modified gravity theories suggested that the familiar gravitational equation needed a small correction, a tweak in how force diminished over vast spans. These concepts were bold, even rebellious, challenging a cornerstone of physics, but the universe's behavior demanded boldness. Yet as data accumulated, the invisibility of this unknown matter became even more convincing. Observations from gravitational lensing revealed distortions in spacetime far too strong to be produced by visible matter alone. Light from distant galaxies was bent into arcs and halos, outlining invisible mass as though tracing the contours of a giant, unseen creature. These distortions matched perfectly with the motions of galaxies and clusters, painting a consistent picture. Something immense and dark was shaping the cosmos. Still, the gravitational riddle was not satisfied with simple acceptance. It continued presenting new complexities. High-resolution simulations of galaxy formation showed that without this mysterious mass, structures would not coalesce into the patterns we observe today. The cosmic web, the vast network of filaments and voids stretching across billions of light-years, required more gravitational glue than visible matter could provide. Without it, galaxies would form too slowly, cluster too weakly, and drift apart too easily. Furthermore, galaxy collisions added yet another layer to the puzzle. The Bullet Cluster, one of the most dramatic cosmic collisions ever observed, showed a clear separation between visible matter and gravitational mass. Hot gas clouds, bright in X-rays, lingered behind as two clusters passed through each other, but the bulk of the gravitational influence moved ahead with the galaxies themselves. This observational stroke was a decisive hint. The universe's invisible component behaved differently from ordinary matter, refusing to collide or slow down. Despite the mounting evidence, the riddle retained its quiet majesty. Even as scientists grew more confident in the existence of this unseen mass, they remained unsure of its nature. Was it composed of exotic particles, remnants of early cosmic processes, or something even stranger, perhaps a reflection of deeper physics yet undiscovered? The gravitational riddle did not merely challenge mass accounting, it challenged the boundaries of imagination. Every telescope, every survey, every gravitational lensing map added more texture to the cosmic enigma. Yet the more clearly the invisible mass was charted, the more elusive it seemed. Its fingerprints were everywhere: curved space-time, stable clusters, fast-spinning galaxies, but the substance itself remained beyond direct detection. It was like hearing footsteps without ever seeing the walker. The riddle extended its reach into cosmology. Measurements of the cosmic microwave background showed subtle patterns, ripples in the early universe, that matched perfectly with a universe dominated by invisible matter. These primordial signatures offered a glimpse into cosmic infancy, reinforcing the idea that this unseen mass had been shaping the universe since before the first stars were born. Even so, alternatives to the invisible mass hypothesis persisted. Modified gravity models continued evolving, addressing new observations with growing sophistication. They offered elegant mathematical descriptions that required no exotic particles, only gentle changes to the law of gravity on large scales. For some scientists, these ideas held a poetic appeal. Perhaps the universe wasn't hiding anything at all, perhaps we were simply misreading the rules. But whether the answer lay in hidden mass or altered gravity, the core mystery remained the same. Galaxies spun too fast, and clusters stayed bound against all expectations. Nature was clearly expressing something profound, and humanity was still learning how to interpret the message. Over time, the riddle shaped entire careers. Generations of astronomers grew up knowing that the cosmos contained more mystery than certainty. Students who first looked through telescopes felt the weight of the unknown pressing gently against them, reminding them that exploration was far from complete. The gravitational puzzle became a symbol of how much remained veiled in the universe's deep silence. The pursuit of answers pushed technology to new heights. More sensitive detectors, more powerful telescopes, more refined simulations all emerged partly because of the desire to solve the gravitational riddle. In an unexpected way, the mystery fueled progress, guiding innovation like a star guiding travelers through the night. The riddle also shaped philosophy. What did it mean that most of the universe was invisible? What did it reveal about human limitations, about the narrow slice of reality accessible to our senses? Scientists began contemplating not just the mechanics of gravity but the nature of existence itself, exploring boundaries where empirical knowledge met metaphysical reflection. In quiet observatories atop cold mountains, researchers continued measuring rotation curves with the same reverence one brings to sacred texts. Each curve, each plot, each data point added a brushstroke to the portrait of a universe that was both familiar and profoundly alien. The cosmos spun its galaxies like dancers defying choreography, held in formation by something unspoken. With each passing year, the gravitational riddle became less a problem to be solved and more a companion to discovery. It reminded scientists that mystery was the engine of progress, that unanswered questions were invitations rather than obstacles. The universe did not owe clarity, it offered clues, and it was up to humanity to learn how to read them. Yet the core enigma remained. Why did galaxies spin too fast? Why didn't clusters tear themselves apart? The answer hovered like a shadow on the edge of understanding, just close enough to sense but too faint to grasp fully. It was a riddle the universe whispered but never shouted. Even as consensus leaned toward unseen mass, the humility of science persisted. Perhaps the invisible matter was real. Perhaps gravity needed revising. Perhaps something no one had yet imagined held the key. The ongoing search embraced all possibilities, grounded in evidence but open to wonder. In the end, the gravitational riddle became one of the cosmos's most beautiful gifts. It revealed that the universe was larger, stranger, and richer than humanity had assumed. It reminded researchers that reality is not bound by expectation, that nature writes its own laws, and that understanding them requires patience, imagination, and a willingness to be humbled by the unknown. And still, galaxies spin. Clusters hold. The invisible force, whatever its true form, continues shaping the universe with quiet strength. The riddle remains not a frustration, but a promise that there is more to discover, more to understand, more to seek in the vast dark that surrounds every star. Early universe clues. How the cosmic microwave background hints at unseen mass begins with a whisper of ancient light radiation so faint and cold that it feels more like a memory than a physical presence. This relic glow, known as the cosmic microwave background, carries the imprint of a universe still in its infancy, just 380,000 years old. Its patterns look like tiny freckles scattered across the sky, slight temperature shifts that might appear meaningless at first glance. Yet within those delicate fluctuations lies a cosmic diary written by physics itself, revealing secrets about how matter first clumped, stretched, and vibrated in the primordial soup. And when scientists began decoding this diary, they found unmistakable hints of something massive, silent, and invisible shaping those early ripples long before galaxies ever formed. As researchers studied these temperature variations more carefully, they realized that the fluctuations weren't random. They followed a subtle rhythm, a cosmic scale of highs and lows caused by waves of pressure, acoustic oscillations rippling through the early plasma of electrons, photons, and atomic nuclei. These vibrations froze into the CMB when the universe cooled enough for atoms to form and light to travel freely. But here was the revelation. The shape, spacing, and intensity of those oscillations could only be explained if a large portion of the universe's matter had not interacted with light at all. Something unseen had added gravitational weight, altering the tempo of the cosmic vibrations. Scientists soon recognized that visible matter alone couldn't produce the patterns seen in the CMB. Ordinary atoms interacted with photons, creating pressure that pushed waves outward, but something else had to be pulling the waves inward, something that tugged gravitationally but didn't collide or scatter light. This invisible contributor anchored the density peaks, deepening the gravitational wells that allowed the acoustic oscillations to grow. Without it, the peaks would appear differently shaped. The entire power spectrum of the CMB would shift in ways that simply didn't match observation. The early universe was sending a message. Unseen mass had been there from the very beginning. Precision measurements from satellites like COBE, WMAP, and later Planck sharpened the picture dramatically. Each mission produced maps with finer detail, revealing temperature contrasts down to millionths of a degree. These maps weren't just beautiful, they were mathematical gold. They allowed scientists to calculate exactly how much matter existed in the young universe and how that matter behaved. What emerged was astonishing. About 5 times more matter existed than could be accounted for by atoms. This invisible mass acted as the scaffolding on which early structures formed, guiding the cosmos toward the galaxies and clusters we see today. The CMB also revealed something remarkable about the timing of cosmic growth. Ordinary matter, interacting with light, was slowed by radiation pressure in the early universe. It couldn't collapse into structures quickly because the photons kept kicking it outward. But the unseen mass, non-luminous, unaffected by light, began clumping far earlier. It laid down the gravitational framework while ordinary matter lagged behind, eventually falling into those invisible wells once photons decoupled. Without this head start provided by unseen mass, the universe would still look nearly smooth today, lacking galaxies altogether. Another clue from the CMB came from a property known as the damping tail, the way fluctuations become smaller at small scales. Ordinary physics alone predicts a certain level of smoothing due to photon diffusion, but the observed damping pattern was too subtle to match a universe containing only visible matter. The presence of unseen mass altered the diffusion behavior and changed how the smallest ripples evolved. Once again, invisible matter left a quiet signature, etched like a faint fingerprint into the fabric of the early sky. Polarization patterns in the CMB added yet another dimension to the story. These polarization signals formed when light scattered off electrons during the last moments before decoupling. The exact orientation of these patterns was influenced by the gravitational wells created by matter, both seen and unseen. The polarization confirmed the temperature data with elegant consistency, offering a second, independent line of evidence that invisible mass had shaped the universe's earliest light. As scientists built more sophisticated models, they realized that removing unseen mass from the equations broke the harmony of the CMB entirely. The peaks in the power spectrum shifted to positions that no observation supported. The relative heights became mismatched. The universe, in equations lacking unseen mass, looked like a badly tuned musical instrument producing off-key tones. Only by including invisible matter could the cosmic symphony align with observation, each peak resonating at the right amplitude and spacing. The CMB also helped identify not just the existence of unseen mass but its behavior. It could not be hot and fast-moving. If it were, the acoustic peaks would smear out. Instead, the evidence pointed toward slow-moving, cold, gravitationally dominant particles, cold dark matter. This inference came not from direct observation but from the quiet logic embedded in those ancient ripples. The early universe had been whispering the nature of its unseen architecture long before anyone knew how to listen. Beyond temperature and polarization, the gravitational lensing of the CMB offered a new window into unseen mass. As the photons from the early universe traveled across billions of light-years, their paths bent around concentrations of matter. By measuring these distortions, scientists could map the invisible mass distribution across cosmic history. These maps aligned with predictions of a universe dominated by unseen mass, matching the CMB's earlier clues with almost eerie precision. Interestingly, the CMB showed that the universe was surprisingly flat. In cosmology, flatness means that spacetime has just the right amount of total mass energy to avoid curving inward like a sphere or outward like a saddle. But visible matter alone couldn't provide the density required for such balance. The early universe's light told us that the missing mass needed to preserve flatness was present, even though telescopes could not see it. As researchers refined their analyses, they used the CMB to determine how much of the universe was made of atoms, how much was made of unseen mass, and how much was made of dark energy. These ratios were not guesses, they were extracted from the precise wiggles in the power spectrum. The early universe, through its faint glow, provided a mathematical confession: ordinary matter was only a small fraction of the cosmic inventory. These discoveries reshaped cosmology, turning unseen mass from a speculative idea into an essential ingredient of the cosmic recipe. The CMB didn't just hint at it, it practically announced its presence in every peak, trough, and polarization twist. The invisible matter wasn't a late addition tacked onto the universe, it was part of the primordial blueprint. Even so, the CMB posed new questions. If unseen mass existed so early, what formed it? Was it created during cosmic inflation, the rapid expansion of the universe? Did it arise from exotic processes in the first fractions of a second? The clues were present but incomplete, like pieces of a puzzle still waiting for their final shapes. The CMB also suggested that unseen mass interacted almost solely through gravity. If it had interacted through electromagnetism, strong forces, or weak forces in ordinary ways, the fluctuations would have looked dramatically different. The early universe served as a natural laboratory, revealing what the unseen mass did not do, narrowing the possibilities for what it could be. Researchers continued comparing CMB data with simulations of structure formation. The results were stunning. Only simulations including unseen mass created cosmic webs resembling reality. The CMB told the beginning of the story, and the cosmic web illustrated its evolution, both pointing toward the same invisible scaffolding. This convergence gave scientists confidence that they weren't following a misinterpretation but uncovering a coherent truth. As experiments improved, the CMB became the benchmark against which all theories of unseen mass were tested. Any proposal for its nature had to reproduce the exquisite detail of the power spectrum. This constraint eliminated countless speculative models, revealing that the early universe was far more precise in its messaging than anyone expected. Even today, the CMB remains a cosmic compass. Every new observation, gravitational lensing surveys, galaxy distributions, cluster dynamics must align with the metrics gleaned from that ancient glow. And remarkably, they do. The consistency reinforces the idea that unseen mass has been a fundamental player since the universe's earliest chapters. Yet the CMB's message remains both clear and mysterious. It tells us unseen mass exists, shapes cosmic evolution, and behaves in specific ways. But it does not reveal what the unseen mass actually is. It outlines the shadow in perfect detail but withholds the identity of the caster. This lingering mystery keeps scientists searching, probing deeper into cosmic signals, particle physics, and beyond. The early universe provided the clues, but humanity must still solve the riddle. The CMB's ancient light continues to shine not just across space, but across curiosity, guiding researchers toward answers that remain just beyond the horizon. In the end, the cosmic microwave background stands as a quiet testimony to the universe's hidden architecture. Its faint ripples encode the story of gravitational wells carved by unseen mass, wells that would one day cradle galaxies, stars, and eventually life. Through those signals frozen in time, the universe gently reveals that most of what shaped its destiny was invisible yet utterly essential. The unseen scaffolding, how dark matter provides the gravitational backbone for cosmic structures, begins with a kind of quiet architecture, an invisible framework woven through the universe long before stars lit the darkness. In the earliest moments after the Big Bang, the cosmos was a hot swirl of particles, radiation, and turbulent energy. Ordinary matter struggled to cling together, constantly pushed apart by the relentless pressure of photons. But dark matter, indifferent to light and immune to these pressures, began forming gravitational footholds. These invisible footholds became the first seeds of structure, tiny wells in the expanding space that gently tugged ordinary matter toward them, guiding the universe's earliest attempts at formation. As the universe cooled, these dark matter concentrations continued deepening. They were not smooth clouds but a complex network of potential wells, shaped by the random fluctuations of the early universe. Because dark matter interacted only through gravity, it flowed freely into these density enhancements, gathering and pooling like water into basins. These basins, called dark matter halos, became the silent hearts around which visible matter would eventually assemble. Without these halos, ordinary matter would remain too evenly dispersed, unable to collapse into stars or galaxies in time to match what we see today. In simulations of the early universe, dark matter displays an astonishing ability to clump efficiently. The particles move slowly enough to congregate but do not collide or radiate energy like atoms, allowing them to retain their structure through violent mergers and rapid expansion. These properties give dark matter a unique stability, turning it into a kind of cosmic skeleton. Without it, the collapse of ordinary matter would be too slow, too fragile, or too chaotic to form the rich tapestry of galaxies and clusters observed across the heavens. As billions of years passed, these dark matter halos grew from tiny specks to enormous structures. Small halos merged into larger ones, forming vast cosmic neighborhoods. The mergers created deeper and more massive gravitational wells, pulling even more ordinary matter inward. These processes were not gentle. The universe roared with collisions and turbulence. Yet through all the chaos, dark matter remained the quiet stabilizer, shaping the gravitational landscapes that allowed order to emerge from primordial disorder. Observations of galaxy formation reveal the unmistakable fingerprint of this unseen backbone. Galaxies appear embedded in halos far more massive than their luminous components. The stars, gas, and dust occupy only the densest central regions, while the dark matter halo stretches far beyond what the eye can see. This halo controls the rotation of the galaxy, its gravitational pull extending to the outermost orbits. Without this extended mass, stars on the galaxy's outskirts would drift away, unable to maintain their circular paths. The structure we see on the largest scales, filaments, clusters, walls, and voids, owes its existence to this underlying dark matter network. If one could strip away all visible matter, the universe would still resemble a vast, interconnected web. This web is composed of trillions of dark matter halos, connected by filaments and separated by enormous empty regions. Ordinary matter later flowed into these filaments like rivers, filling the channels carved by tectonic forces, illuminating the shape dark matter had already drawn. Clusters of galaxies provide some of the strongest evidence for dark matter's structural guidance. These massive cosmic cities contain thousands of galaxies bound together by a gravitational pull far stronger than visible mass can provide. Hot gas within clusters emits X-rays, and its temperature reveals the cluster's total mass. Yet the visible galaxies and gas account for only a fraction of this mass. The rest resides in a colossal dark matter halo that stretches across millions of light-years. Without this unseen scaffolding, clusters would simply not hold together. Even more compelling is the bullet cluster, where a high-speed collision between two clusters separated ordinary matter from the dark matter halos. The hot gas collided and slowed, producing a brilliant X-ray signature that lagged behind. But gravitational lensing revealed that most of the mass had already passed through, unaffected by collisions. This separation illustrated the independent existence of the dark matter framework holding each cluster together, demonstrating that it does not behave like ordinary matter at all. Galaxy formation itself depends critically on the properties of dark matter. Ordinary matter cools by radiating energy, falling deeper into the dark matter halo where it can condense into stars. Without halos providing gravitational basins, gas clouds would struggle to collapse efficiently. Simulations excluding dark matter show that galaxies either fail to form or form far too slowly, producing structures incompatible with observations. The universe we know would simply not exist in its recognizable form without the scaffolding dark matter provides. As galaxies formed, they did so around the densest cores of their halos. These cores became the cradles of stellar birth. Over time, gas spiraled inward, cooled, and ignited into the first stars, lighting the universe for the first time since the Big Bang. But even as stars formed, they never dominated the mass of the galaxy. They floated like fireflies within a much larger, invisible sphere whose gravitational influence dictated the galaxy's growth, shape, and stability. As galaxies merged, the dark matter halos merged as well. These mergers shaped the hierarchical evolution of structure, with small galaxies combining to form larger ones. The halos blended into ever larger gravitational envelopes, providing a stable environment in which galaxies could continue forming new stars. In many cases, the dark matter dominated the outcome of the merger, influencing the final distribution of stars and the overall morphology. On even larger scales, Dark matter's influence guided the formation of superclusters, massive conglomerations of galaxy clusters linked by dark matter filaments. These superclusters stretch across hundreds of millions of light-years, forming the largest structures known. They are bound not by ordinary gravitational interactions alone, but by the deep gravitational wells carved by dark matter. Every filament connecting them is enriched with dark matter, serving as pathways for galaxies to flow along during cosmic evolution. The cosmic web we observe today matches beautifully with simulations that include dark matter. When scientists generate models based solely on visible matter, the resulting universe looks empty, flat, and nearly featureless. But when dark matter is added, the universe blossoms into a complex network nearly identical to what telescopes reveal. The distribution of galaxies, their clustering patterns, and their motions all emerge naturally from simulations rooted in dark matter's gravitational influence. Even the shapes of galaxies reflect the halos that cradle them. Spiral galaxies like the Milky Way sit within relatively calm halos that allow thin disks to form. Elliptical galaxies, by contrast, often arise in halos that have experienced more violent mergers. Thus, the history of dark matter halos becomes the history of the galaxies they host, weaving the invisible and visible components into a shared narrative of cosmic evolution. One remarkable aspect of this unseen scaffolding is how it shaped the universe long before ordinary matter played any visible role. Dark matter's early gravitational clumping created the initial blueprint for cosmic architecture. When the first atoms formed, they simply fell into the pre-existing wells, populating the invisible framework like dew gathering on the branches of a vast, unseen tree. The visible universe grew as a delicate layer atop a much larger, older, and more stable foundation. Gravitational lensing allows astronomers to map this unseen scaffolding directly. As light from distant galaxies travels toward us, it bends around the massive halos in its path. These distortions, subtle yet measurable, create maps of dark matter distribution that align with theoretical predictions. In effect, the universe reveals its skeleton through the way it bends light, enabling scientists to trace the hidden filaments that structure the cosmos. Another fascinating property is that dark matter halos continue to grow even today. Though galaxy formation has slowed, halos are still merging, absorbing smaller halos, and reshaping their gravitational boundaries. This ongoing accretion ensures that cosmic structure remains dynamic, with galaxies slowly migrating along filaments like travelers moving through ancient, invisible highways carved by gravity. The interplay between dark matter and dark energy further shapes the cosmic framework. Dark matter pulls structures together, while dark energy expands space itself. The competition between these forces determines the fate of the cosmic web, whether it continues growing, stabilizes, or gradually stretches apart. For now, dark matter's grip maintains the integrity of galaxies and clusters even as dark energy accelerates cosmic expansion. Even though dark matter is unseen, its influence permeates every cosmic process. Star formation rates depend on halo growth. Galaxy mergers follow the paths laid by halos. The distribution of heavy elements, the heating of intergalactic gas, and the evolution of galaxy shapes all trace back to the gravitational template carved by dark matter. To understand the visible universe is to understand the invisible one first. Yet despite its decisive role, dark matter remains elusive. Scientists know how it behaves but not what it is. Its identity is a puzzle composed of gravitational clues, scattered across cosmic structures. Every simulation, observation, and theoretical model hints at a deeper truth waiting to be uncovered. And although the scaffolding remains unseen, its presence is undeniable, shaping the universe with silent authority. In the end, the cosmic structures that fill the night sky, spiral galaxies, massive clusters, glowing filaments, are only the luminous decorations on a grander, invisible frame. Dark matter is the unseen scaffolding that holds the universe together, guiding the flow of matter, light, and time itself. Through its gravitational embrace, the universe found stability, complexity, and the possibility of stars, planets, and life. Its silence is not emptiness but the quiet strength of the architecture that underlies everything. Dark matter remains invisible to our eyes, yet across the quiet, dim reaches of the cosmos, scientists use space telescopes to search for subtle hints of its presence, especially in the delicate traces of particle annihilation. They cannot see the dark matter itself, but they can look for the products of its possible interactions, gamma rays, neutrinos, and other high-energy messengers that drift silently across interstellar space. Each telescope becomes a patient listener, waiting for a whisper in the cosmic dark. As these telescopes scan regions like the galactic center, dwarf galaxies, and massive clusters, researchers hope to catch patterns that regular astrophysical processes cannot easily explain. The logic is simple yet profound. If dark matter particles annihilate or decay, they should produce signals that stand out from the usual cosmic background. But in practice, separating the unusual from the ordinary becomes a meticulous, almost meditative process that takes years of comparison, modeling, and reanalysis. The Fermi Gamma Ray Space Telescope has become one of the most important tools for this work, constantly monitoring the sky for high-energy flashes that might hint at dark matter events. Its observations allow scientists to map the sky in gamma rays and search for regions where the energy signature matches theoretical predictions. But gamma-ray astronomy is noisy, full of pulsars, supernova remnants, and jets from active galactic nuclei, each trying to masquerade as something more exotic. By comparing the gamma-ray glow of dwarf spheroidal galaxies, places with very little normal matter but a high ratio of dark matter, researchers attempt to tease out whether an excess of light exists. These faint galaxies, often dim and ghostly, act as natural laboratories, offering a clearer stage where the interplay of dark matter might leave its faint footprint without being drowned out by the fireworks of stellar processes. Neutrino detectors, although not space telescopes themselves, complement this cosmic search by listening for nearly massless particles arriving from deep space. If dark matter concentrates in dense regions like the center of the Sun, annihilation could create neutrinos that escape into space. Space-based and ground-based observatories combine their findings, layering evidence like thin sheets of glass to form a clearer picture. In addition to gamma rays and neutrinos, telescopes such as Chandra and XMM Newton observe X-ray emissions that may also hint at exotic dark matter behavior. One famous example is the mysterious 3.5 keV line discovered in several galaxy clusters, a faint spike in X-ray spectra that sparked debates about whether it could originate from the decay of a hypothetical dark matter particle. The scientific community still wrestles with this possibility, as every new observation adds both clarity and confusion. The challenge lies not only in detecting faint signals but in constructing theoretical models that explain them without contradicting known astrophysics. Dark matter searches often find themselves tangled with the complexities of cosmic structures, star formation, black hole activity, and energetic jets that produce similar signatures. Distinguishing between astrophysical noise and genuine dark matter signals requires patience, skepticism, and an ever-evolving set of analytical tools. Some space telescopes focus more on precision mapping than direct detection, creating detailed surveys of cosmic structures that may reveal regions where dark matter interactions are more likely. The more precisely we map the mass distribution of the universe, the easier it becomes to predict where annihilation should be strongest. These predictions then guide telescopes toward promising cosmic neighborhoods. The concept of annihilation itself emerges from certain dark matter theories, especially those involving weakly interacting massive particles, WIMPs. If these particles collide with one another, they may release energy in predictable forms. Telescopes tuned to detect those energy forms scan the sky for patterns that match these expectations. But so far, every hint remains ambiguous, balanced between possibility and uncertainty. Even when a telescope records a promising signal, scientists repeat the analysis under different conditions, using updated background models and alternative assumptions. This careful repetition ensures that the result is not a statistical fluke or misunderstanding of galactic behavior. The cosmos rarely offers simple answers, and dark matter, being invisible, forces researchers into a detective-like mindset, reconstructing unseen events from faint clues. Future missions hold enormous potential. Projects like the Cherenkov Telescope Array, though ground-based but deeply complementary to space telescopes, will sharpen the search for high-energy gamma rays with unprecedented sensitivity. Combined with next-generation space observatories, scientists hope that these instruments will finally push the boundaries enough to reveal something unmistakably non-ordinary, something that cannot be explained away so comfortably. Space telescopes studying the early universe might uncover indirect evidence through the patterns of structure formation. Dark matter influences when and how stars and galaxies formed, and subtle distortions in the cosmic background radiation or large-scale structure surveys could reveal energy injections from annihilation in the early universe. These signals, preserved across billions of years, become fossils of ancient cosmic behavior. Some researchers focus heavily on the galactic center, believing it to be one of the richest containers of dark matter. The region glows with gamma rays, and some studies have claimed there is an unexplained excess. But disentangling dark matter from the tumult of pulsars, supernova remnants, and high-energy cosmic processes makes the analysis exceptionally difficult. Still, the galactic center acts as a gravitational cauldron that demands ongoing observation. As telescopes continue collecting data, collaborations across nations and disciplines grow stronger. Data from one observatory feeds theoretical models implemented by another team, while simulations refine the predictions for where the next set of telescopes should look. This synergy between instruments and minds becomes as important as the observations themselves. One of the subtle beauties of indirect detection is that it turns the universe itself into a laboratory. Instead of creating particles in controlled accelerators, scientists let the cosmos perform the experiment naturally, observing the outcomes through its immense and ancient machinery. The stars, clusters, and voids become part of the great apparatus, revealing their hidden workings in faint energies. Some of the most promising dark matter candidates produce narrow spectral lines, bright, thin features in energy distributions that cannot be easily mimicked by regular astrophysics. Telescopes search obsessively for such lines, knowing that even a single confirmed detection could rewrite our understanding of particle physics. But nature remains coy, offering hints that dissolve under scrutiny. The search also pushes technology forward. To detect faint gamma rays or X-rays, telescopes must shield themselves from background noise, employ detectors of exquisite sensitivity, and maintain stable, ultra-quiet environments. Every improvement in instrumentation deepens our ability to listen to the universe, like refining a musical instrument so that even the softest note becomes audible. Meanwhile, simulations running on supercomputers help scientists predict the patterns of annihilation under different dark matter models. They generate maps of anticipated gamma-ray halos, energy distributions, and time-varying patterns. Space telescopes then compare these maps with real observations, narrowing the field of possible models and guiding the next wave of theoretical innovation. Indirect detection is not limited to high-energy particles alone. Some theories predict that dark matter interactions might subtly alter the temperature or ionization state of intergalactic gas. Telescopes like Planck and upcoming missions look for these extremely delicate fingerprints imprinted on the large-scale structure and cosmic background radiation. Through all these methods, the search for dark matter becomes a story of persistence. Each year, observations grow more precise, models more sophisticated, and hopes more refined. Yet the cosmos preserves its silence, offering clues without answers, patterns without explanations. The process becomes an ongoing conversation between humanity and the stars. What keeps scientists striving is the sense that they are close, perhaps not close chronologically, but close conceptually. The universe behaves as if something massive and invisible permeates it. Gravity reveals its touch everywhere. And so space telescopes, with their sensitive eyes, continue scanning, hoping for the one unmistakable signal that would break the silence. Indirect detection thus becomes a blend of subtlety, patience, and imagination. The signals are faint, the universe vast, and the physics uncertain. But each observation, each anomaly, each unexplained spike in a distant spectrum pushes humanity closer to understanding the dark undercurrent shaping the cosmos. And so the search continues, quietly and endlessly. Even without a confirmed detection, the process yields value. It constrains models, eliminates incorrect ideas, and sharpens our understanding of cosmic structures. These boundaries guide future creativity, ensuring that the next generation of theories is rooted firmly in observation rather than wishful thinking. The quiet hum of space telescopes continues, gathering photons that have traveled millions or billions of years. Somewhere in that enormous archive of cosmic messages may lie the first true sign of dark matter annihilation. But until it emerges clearly, scientists embrace the uncertainty, allowing curiosity to carry them through the long nights of analysis and reflection. Space telescopes searching for dark matter annihilation operate almost like detectives of the cosmos, gathering faint clues rather than direct sightings. Dark matter itself does not emit, reflect, or absorb light, so telescopes must look for secondary signals, energetic byproducts that might appear if dark matter particles annihilate or decay. These telescopes scan the sky for unusual gamma rays, neutrinos, or X-ray features that cannot be accounted for by known astrophysical processes. In this indirect search, every photon is examined like a piece of evidence in a case that has haunted astronomy for decades. The Fermi Gamma Ray Space Telescope is one of the primary instruments tasked with this mission. It constantly observes the high-energy sky, capturing bursts, glows, and patterns of gamma rays that may originate from exotic particle interactions. When researchers observe a region where gamma rays exceed the expectations from ordinary astrophysical sources, they consider whether dark matter might be at work. But separating a potential annihilation signature from the chaotic background of collapsing stars, pulsars, and black hole jets becomes a delicate, highly technical puzzle requiring endless refinement. Among the most promising targets for indirect detection are dwarf spheroidal galaxies. These faint, small companions of the Milky Way contain very few stars but large amounts of dark matter. With less stellar activity to muddy the signals, any excess gamma rays observed from these galaxies stand out more clearly. Scientists repeatedly return to them, analyzing their emissions with increasing sensitivity, hoping for the one unmistakable pattern that would reveal dark matter's presence. Yet so far, every hint has dissolved under stricter scrutiny. Another major region of interest is the galactic center. It is believed to host one of the densest concentrations of dark matter in the Milky Way, making it an ideal location to search for annihilation signals. However, the galactic center is also extraordinarily active, crowded with pulsars, supernova remnants, and energetic interactions that produce similar gamma-ray emissions. This creates an observational fog that telescopes must peer through, challenging scientists to build complex models that disentangle possible dark matter signatures from the astrophysical chaos. Neutrino observatories complement space telescopes by listening for nearly massless particles that could be produced by dark matter annihilation. These elusive particles travel unimpeded across cosmic distances and might originate from dark matter trapped in massive bodies like the Sun. If dark matter accumulates in the Sun's core and annihilates, it could produce high-energy neutrinos that escape and reach detectors on Earth. While not a space telescope in the literal sense, this method harmonizes with the broader search, offering another indirect avenue to identify dark matter interactions. X-ray telescopes such as Chandra and XMM Newton participate in the search by looking for unexpected lines in the X-ray spectrum. One such example is the mysterious 3.5 keV line observed in several galaxy clusters, a faint yet intriguing spike in energy that sparked debates across astrophysics. Some argued that it could be the signature of a decaying dark matter particle, while others suggested it might stem from previously misunderstood atomic processes. The debate persists, and each new observation across different environments adds tension to the question without settling it. The challenge with indirect detection lies in modeling the background, understanding every other possible source of the observed radiation. The cosmic sky is full of energetic phenomena, and many of them can imitate the expected signals of dark matter annihilation. Pulsars, for example, produce gamma-ray emissions that can mimic a dark matter-induced glow. Black hole accretion processes, stellar winds, and supernova remnants all contribute to the tapestry of the high-energy universe, weaving together patterns that telescopes must unravel with patience. To enhance their effectiveness, telescopes rely on theoretical predictions generated from sophisticated simulations. Supercomputers model galaxies as vast swarms of dark matter particles, computing where annihilation signals would be strongest and what their spectral shapes might look like. The resulting maps guide observational strategies, allowing telescopes to prioritize regions where detection is statistically more probable. These simulations act as blueprints for the cosmic search, crafted by physics and refined by data. Future observatories promise sharper insights. The upcoming Cherenkov telescope array, though ground-based, will work hand-in-hand with space-based missions to study high-energy gamma rays with unmatched precision. Its sensitivity may help distinguish subtle dark matter signals from conventional astrophysical processes. Planned space missions will further push the boundaries, offering deeper surveys, finer resolution, and improved detectors designed to reduce instrumental noise and catch the universe's faintest whispers. Indirect detection also extends to the early universe, where dark matter may have played a role in shaping cosmic structures through energy injections from annihilation. Space telescopes studying the cosmic microwave background look for slight distortions, temperature variations, or ionization anomalies that could hint at these ancient events. These clues, preserved in the oldest light in the universe, provide a unique portal into interactions that may have occurred billions of years before stars or galaxies existed. Astronomers often search for narrow spectral lines, distinct, sharp features in energy distributions that cannot easily emerge from ordinary astrophysical processes. A confirmed line with the correct properties would be strong evidence for particle annihilation or decay. Even a faint detection would revolutionize cosmology and particle physics. But despite numerous attempts, no such line has yet withstood the rigorous scrutiny required for scientific certainty. The search encourages technological innovation. Detectors must be extraordinarily sensitive, capable of distinguishing a small number of photons from a massive background of noise. Space telescopes require precise calibration, shielding from cosmic rays, and advanced electronics to measure faint energies accurately. Each improvement pushes the observational frontier further, allowing scientists to probe what was previously unreachable. Despite the challenges, the indirect search illuminates the universe in unexpected ways. In trying to distinguish dark matter from conventional astrophysics, researchers learn more about pulsars, supernovae, black hole accretion, and the intricate workings of galaxies. Even the absence of a confirmed detection refines the models, narrowing the range of possible properties dark matter might possess. These constraints shape the next generation of theories and guide new experiments. Another promising approach involves studying galaxy clusters, the largest gravitationally bound structures in the universe. Their enormous dark matter content makes them ideal candidates for annihilation signals. Telescopes map their gamma-ray and X-ray emissions, searching for anomalies that could hint at dark matter processes. Each cluster provides a different environment: cool core clusters, merging clusters, and relaxed clusters, offering diverse opportunities for indirect detection. Scientists also analyze diffuse gamma-ray backgrounds, the ever-present glow that fills the sky. If dark matter annihilation contributes to this background, its fingerprints might be detectable through statistical patterns. By carefully modeling known sources and subtracting their contributions, astronomers hope to isolate the faint residue of dark matter's influence. This method requires enormous datasets and meticulous cross-checking, but remains one of the most promising large-scale strategies. Space telescopes sometimes detect unexplained excesses, subtle enhancements in energy ranges thought to be associated with dark matter. These excesses spark intense debate, with teams around the world analyzing the same data using different methods. The process becomes a scientific dialogue shaped by skepticism, enthusiasm, caution, and creativity. Each possible signal becomes an intellectual battleground where evidence must withstand the sharpest challenges. Indirect detection illustrates the universe's complexity. Even with the most sophisticated telescopes, the cosmos rarely offers clean, simple signals. Instead, it presents overlapping phenomena, energetic bursts, and long-lived remnants of ancient events. Researchers must piece together this cosmic mosaic, aware that one small misinterpretation can create an illusion of discovery. This humility strengthens the scientific process and prevents premature conclusions. Collaborations form a major backbone of this field. Teams spanning continents share data, models, and simulations. One telescope's findings must be cross-checked with those of another. If a gamma-ray excess appears in one instrument, neutrino detectors and X-ray observatories may follow up. This multi-messenger strategy increases confidence and helps determine whether a signal is truly extraordinary or simply misunderstood background behavior. Indirect detection is often described as a search for a whisper in a storm. The storm is the chaotic, energetic universe filled with countless astrophysical processes. The whisper is the faint trace of dark matter's hidden interactions. To isolate it, scientists patiently refine their models, improve their instruments, and revisit earlier observations with fresh perspectives, software, and theoretical frameworks. Some theories predict that dark matter might annihilate more efficiently under certain conditions, such as in regions of extreme density or at specific energies. Telescopes tuned to these energies search for features, small bumps, spectral distortions, or time-independent glows that match the predicted shapes. These searches continue year after year, building an archive of data that future scientists can reinterpret using better models and improved understanding. The study of cosmic rays also enters the indirect detection landscape. If dark matter annihilates into charged particles, it could influence the cosmic ray spectrum measured by instruments like AMS-02 aboard the International Space Station. Although not a traditional telescope, this experiment plays a complementary role by searching for anomalies in the flux of positrons or antiprotons. Some deviations have been found, sparking debates about whether they arise from dark matter or nearby astrophysical sources like pulsars. The universe serves as a vast natural collider, performing particle interactions at energies far beyond those produced in human-made accelerators. Indirect detection takes advantage of this cosmic machinery, using telescopes as observatories of naturally occurring high-energy physics. The distant reaches of space become laboratories where exotic processes might unfold, offering a unique opportunity to explore fundamental physics on a grand scale. Despite the continued lack of definitive evidence, the field remains optimistic. With each passing year, telescopes grow more sensitive, datasets expand, and our understanding of astrophysical backgrounds improves. The search tightens around the remaining viable dark matter models, slowly restricting what dark matter can and cannot be. This gradual progress builds the foundation for future breakthroughs. The pursuit of indirect detection reflects humanity's enduring curiosity and persistence. It is a long game, one that may take decades to yield a clear result. But the steady accumulation of knowledge, the refinement of instruments, and the collaboration of hundreds of scientists across the world ensure that the search continues with determination. And somewhere, hidden in the faintest energy signatures, the universe may yet reveal the long-sought proof of dark matter's elusive nature. Dark matter continues to dominate cosmological thinking because every attempt to replace it with a simpler alternative collapses under the weight of observational evidence. Modified gravity theories, elegant as they may seem, often explain one phenomenon only to conflict with another. They might fix galaxy rotation curves but fail to account for the behavior of galaxy clusters or the imprint left on the cosmic microwave background. Each observation becomes a test, and most alternatives stumble when held against the full suite of cosmic data. The universe appears to be whispering a consistent story that there is more mass than meets the eye. When astronomers map the rotation curves of spiral galaxies, they find a compelling pattern. Instead of slowing with distance from the center, stars maintain unexpectedly high orbital speeds. Modified gravity theories can fine-tune equations to match these curves, but doing so usually demands different tweaks for different galaxies. Dark matter, on the other hand, offers a universal explanation, a massive